Good day everyone, this is the continuation of our Module 2.1, wherein we will discuss the hypothesis testing for the proportion and hypothesis testing for the standard deviation and our variance, okay? So before we start our Module 3.1 Part 2, so let me just clarify things in order for us not to be confused about on how we can make decisions on our hypothesis testing, okay? So let's go back to our sample problem here. So let's uh, to the z-test. Okay. Yesterday or excuse me, last Wednesday, okay, so I said a certain uh, condition on how we can determine or decide if our hypothesis will be rejected or fail to rejected. Okay, last time I said that if your z-test, okay, is less than your z-critical, okay, the null hypothesis will be fail to reject. Okay, excuse me. On the other hand, if your z-test, okay, is greater than your z critical, you are going to reject your hypothesis. Okay, this condition, okay, can be only applied, okay, on positive values on the right tail. Okay, so the correct way on how we will decide, or I mean it's correct, but the most precise way in order for us to decide wherein we will reject or fail to reject is by looking at the critical values. Okay, so let's go back to this statement here. Okay, like I said last time, okay, so if the standardized test statistics, so this standardized test statistics, okay, it is our z test or t test. Okay? It is the computed z-test or t-test based on our central limit theorem. Okay? So if the value of our z-test or t-test is in the critical region, okay? Critical, I mean rejection region, wherein this rejection region, okay, is our z-critical or t-critical. Okay? Then reject the null hypothesis. On the other hand, if the z-test or t-test value is not in the rejection region or is not in the region wherein there is a value of z-critical or t-critical, then we can fail to reject our null hypothesis. Okay, so for example, so let's use this example. Okay, so let's start with the single tail. Okay, so for example, the value of our z critical here is 1.645. Okay, so therefore the tail, so here's our 0. Okay, so here's our 0. So the value of our z critical is 1.645. So this is the critical region. Okay, okay, then our computed z-test or standardized test statistic is 1.316. Is 1.316 is in the region of 1.645 onwards? Okay, the answer is no. Therefore, if the value of your test statistics is not in the critical region, so our critical region here is the gray here. So the z-test value is not in the gray area. Therefore, we can conclude that we are failed to reject the null hypothesis, because based on the statement here, okay, if the standardized test statistics or our z-test or t-test is not in the rejection region, then we are failed to reject our null hypothesis. Okay? So on the other hand, if our value of our z-test or t-test is in the rejection region, therefore we can reject a certain null hypothesis. Okay? So let's have an example in terms of we can reject a certain Null hypothesis. Okay, so this example, okay, so our t-test here is negative 4.3481. Okay, and our t-critical or our standardized test statistic is equal to negative 2.262. Okay, so our t-critical starts from negative 2.262. So this is 0. Okay, so always remember that if your value is bigger but it is in negative, therefore it is in or it is smaller, okay? Because it is much farther from 0, okay? So if our T critical, okay, so our region is this color gray. Okay, so our T critical is negative 2.62. So all the values from negative 2.62 onwards to the left is considered in critical region. So if our value is negative 4.3841, therefore we can conclude that we can reject the null hypothesis because the value of our standardized test statistic or t-test value is in the critical region. Okay? So you can remember, or you can uh, you can study or you can memorize or familiarize the conditions that I said last time, but it is only for the right tail test. Okay, so we have also for the left tail test. Okay, so in order for us to summarize this, so we have this clarification. Okay, so reject null hypothesis if t-test is in t-critical region. Okay, so like I said earlier, fail to reject null hypothesis if the t-test is not in the critical region. Always remember, if the value of your t-test or z-test is not in the critical region, automatic, you will fail to reject. On the other hand, if the value is inside the critical region, okay, you should what? Reject it. Okay? So reject null hypothesis if z-test is in z critical region. On the other hand, we are failed to reject the null hypothesis if the z-test is not in the critical region. Okay? So please remember these terms. Okay? So right tail test, so like I said earlier, so we can reject our null hypothesis if our z-test is greater than our z critical. So for example here, we have for example we have a value of z critical is equal to 1.35. Okay, so example, we have z test is equal to 1.5. Therefore we can reject the z test, we can reject the null hypothesis, okay, because the z test value is much greater, and if we have right tail test and if the value of the z test is greater, therefore it is inside the critical region, because the critical region, so the value of your z critical here, all the values from 1.35 up to infinity is considered as inside a certain region. Okay, therefore we can reject the we can reject the null hypothesis because the z-test value is inside the critical region. Okay. Okay, so let's erase this. So on the other hand, for example, we have a value of z critical, we can say 1.2. Okay, and the value of your z-test, for example here, so the value of our z-test is equal to 0.9. Okay, we can conclude that we are failed to reject our null hypothesis here because the value of our z-test is not inside the z critical. Okay, so in short, if the z-test is less than the z critical, so for example here the 0.9 is less than 1.2, okay, we are failed to reject because again the value of our z-test is not inside the rejection region, wherein the rejection region is 1.2 onwards, okay, up to infinity. Okay, so that's so simple as that. It's so simple as that, okay. So note, z can be also t if you're going to use the t-test. So it's just the same. So if z-test, z critical, z-test. If t-test, we have t-test and t-critical. Okay? On the other hand is we have the left-tailed test. Okay, so reject null hypothesis if our z-test, okay, is less than z-critical. Okay, so how can we prove this? For example, our z-critical is negative 2.1. Okay, and our t-critical, okay, next, if our t-critical, z-critical, so our z-critical here is negative 2.1. Okay, next is if we have, okay, for example, we have z-critical here, our z-test is equal to negative 1.2. Okay, so this is our z-test. Okay, so for example, this is our z-test. Okay, this is our z-critical. So for example, the value of our z-test is negative 1.2 and the value of our z-critical is negative 2.1. Therefore, the critical region is from negative 2.1 up to negative infinity. Therefore, this example is failed to reject the null hypothesis, okay, because the value, okay, of your z-test is greater than negative 2.1. Always remember, guys, in terms of negative, the value is greater if it is close from 0. Okay, so in our case, negative 1.2, it's much closer to 0 rather than negative 2.1. Okay. On the other hand, okay, let me just erase this. Okay. For example, our z-critical is equal to 2.2. Okay, and our z-test is equal to negative, we can say negative 4.5. Okay, so we can reject the null hypothesis if the value of our z-test is less than the z-critical. Okay, so like I said earlier, okay, if the value, okay, is much closer to 0, it is what? The greater value in terms of negative. Therefore, we proven that if the z-test, okay, is less than negative 2.2 or our z-critical, we can reject the null hypothesis. Okay? That's so simple. Okay? Please remember, guys, we can reject a certain null hypothesis if it is inside a certain region, and we are failed to reject if it is not in the region. Okay? So that's the simplest way on how to understand, but you can also use these conditions. Okay, so they are just opposite to each other. Okay, and lastly, for the two-tailed test, in terms of the two-tailed test, we will use the combination of the two. So we can use the conditions for the right-tailed and the condition for our left-tailed. And always remember, guys, again, if the z-test value is in the critical region, reject null hypothesis. On the other hand, if the z-test value or any test value is outside the critical region, automatic, we are failed to reject. Okay? Please note here, so the conditions will depend in the value of your test statistics, whether it is negative or positive. Okay? So if your calculated value, okay, of your test statistic, so our test stats can be Z or T. Okay. So the conditions will depend in the value of your test statistics. For example, here in our two-tailed. Okay. So for example, we calculated a value of negative. Okay. So we calculated a value of negative 4.348. So it means we will use, okay, we will use the conditions for the left-tailed. Okay, always remember, in terms of left-tailed, we have negative. In terms of right-tailed, we have positive. Okay? So this is for the negatives. Okay. So let's have a two-tailed example again. Okay. So here we have positive. So in our case, we depend on what? The positive value. So for the example, so our Z critical is 2.58 and our Z test value is 1.0082. So we are failed to reject this example because the value of our Z test, okay, is not in the critical region, because the critical region starts from 2.58 onwards to infinity. Okay? Please remember on how we can determine, or how can we decide whether to fail to reject or reject a certain hypothesis, null hypothesis. Okay? So I think it's cleared now. Okay? So now we will continue our lesson for module 3.1. Okay? So next lesson is we have the hypothesis testing for the P, or the proportion. Okay. So the Z test for a population is statistical test for a population proportion. Okay. The z-test can be used when a binomial distribution is given such that NP is greater or equal to 5 and our NQ is equal to, NQ is greater or equal to 5. Okay? So the test statistic is a sample proportion. Okay? So the test statistics is called is the sample proportion of our P hat. Okay? We're in P hat. Okay, guys, if we remember, P hat is equal to X over N, wherein X is the number of successes and the N is the sample size. Okay? And always remember, our Q is equal to 1 minus P. So in order for us to prove that we can use a certain z-test, okay, for a population hypothesis testing, okay, all we need to do is to prove it by using this condition. So, and if the value of NP is greater or equal to 5 and the value of NQ is greater or equal to 5, therefore we can use this formula. Okay, wherein the P hat is equal to X over N, or number of successes over the sample size, P is the population proportion, and N is our sample size. Okay, so population proportion, okay, so it can be a percentage, fraction, or decimal. Okay, so let's have an example here. An educator estimates the dropout rate for seniors at high school in Ohio is 15%. Last year, 38 seniors from a random sample of 200 Ohio seniors withdrew. So at A is equal, or alpha is equal to 0.05, is there enough evidence to reject the educator's claim? So verify that the products NP and NQ are at least 5. So our N is equal to 200 and P is equal to 15%. So if we convert this to decimal, so we have 0.15. Okay? So before we start our calculation, first we need to prove that we can use the formula. So like I said earlier, so if our NP is greater or equal to 5 and NQ is greater or equal to 5. So we have this proving here. So N, so 200 multiplied by 0.15 or 15%, so we have 30 here. So 200 multiplied by 1 minus 0.15, because like I said earlier, P is equal to, so we have Q is equal to 1 minus P. Okay, so we have 200 multiplied by 1 minus P, or 1 minus 0.15, therefore we have 170. So we proven that we can use the formula given earlier. Okay. So what is the claim here? Okay, so an educator estimates that the dropout rate for senior at high school in Ohio is 15%. Okay, so like I said, the claim can be found in the last part or the first part. So, but in this case, so is there enough evidence to reject? So if we have the word reject, automatic is not equal. Okay, therefore, our alternative hypothesis is we have P, okay, is not equal to, it's our value, 15%. Okay, so and then our null hypothesis, P is equal to 15%. Is it correct? Okay, so we will just convert this to decimal. So in our example, it is shown as 15%. Okay. Step number 3 is to find the critical values. Okay, so we have 0.05, so we have two-tailed. So like I said last time, in terms of alpha, okay, we need to multiply it by 2 if we are going to have two-tailed. So we have alpha over 2. So we have 0.05 divided by 2. So we have 0.025. And the next step, we will use the Z table. Okay, so in our case, like I said, in terms of two-tailed testing, we will depend on the negative value. Okay, and we will just assume that the value in the negative is just the value or the opposite value in the positive region. So if this is negative 1.96, this will be positive 1.96. So let's look at the table. Wait a minute. Where's my table? Okay. So let's look at the negative Z table. Okay. So we need to find the value that is closest to 0.025. Okay. So 0.025. So we have negative 2. So what's the value? 1.96. Okay, so we have here 0.025. So it is under. So we have 0.025 here. So where's the pen? Okay. So we have 0.025 here. Therefore, it is under negative 1.9 and 0.06. Therefore, okay, we have negative 1.96. And like I said earlier, okay, we started with the negative, therefore we will just assume that the value is positive on the right side. Okay, so in our two-tailed, so we have positive, negative 1.96 for the two-tailed here. So next is to calculate the test statistics. So we have the formula p hat. So we have z is equal to p hat, okay, minus p all over square root of pq all over n. Okay, wherein our p hat is equal to x over n. So our x here is 38 and our n is 200. Then we calculate it. We have this value 1.5842. The next step is we need to find the p-value here. So like I said last time, we will use the calculator here. So let me just show my calculator. Okay, so go to setup mode, stat number 3, AC, so shift number 1. So we have distribution number 2 for the Q. So what's the value? So we have 1.5842. Okay, so we have the value for the Q. So shift store. So let's store it to A. Okay, so it is now stored to A. So let's continue. So we have 1 minus quantity 2 times the value of Q, value, so alpha A. So we have 1 point. So the p value is we have 1.1314. So okay, so we have 1.131. So here we have 1.131. Okay, so the value of our test statistics is 1.58. Okay, and the value of our critical value is 1.96. So based on this assumption, okay, can we conclude that the null hypothesis is failed to reject? Yes or no? The answer is yes, because the test value is not in the critical region. Okay, because the critical region starts from 1.96 up to infinity. Okay, so since z-test, okay, so the z-test is 1.5842 is less than the z-critical, okay, and the p-value 1.1131 is greater than our alpha or 0.05, okay, we can conclude that we are failed to reject this hypothesis. Okay, but in terms of p or p-value, okay, always remember to follow the condition. So no changes about the p-value condition. So if it is greater than the alpha, failed to reject. If it is less than alpha, reject the null hypothesis. Okay? Example number 2. A telephone company representative estimates at 40% of each customer call waiting service. To test this hypothesis, she selected a sample of 100 customers, okay, and found, okay, that 37% had call waiting. At alpha is equal to 0.01, okay, is there enough evidence to reject the claim? So verify that the products NP and NQ are at least 5. So let's verify the value. So our N here is 100 because we have a sample size of 100 customers, okay? And our P, so what's the value of our P here? So we have proportion of 40%, okay? So we have 0.4 here. And the Q, like I said, Q is just Q is equal to 1 minus P, okay? So our NP is 40, so it is greater than 5, yes. And our NQ is 60, so it is greater than 5. The answer is yes. Therefore, we can use the approach and the formula for the test statistics. Okay. So what is the claim here? So the telephone company representative estimates that 40% of its customers. Okay, so our alternative hypothesis here is what? We have P is not equal to 0.40, okay, and our null hypothesis is P is equal to 0.40, okay. So don't be confused about this word claim, okay. The most important thing is we all know that the null the hypothesis is okay. So if we have alternative, no inequality. If we have null hypothesis, we are dealing with equality. Okay, so don't be confused about this claim. Okay, so we are done with step 1 and step number 2. So we already determined or specified the null and the alternative hypothesis. Okay, so step number 3 is to find the critical value. So we are dealing with two-tailed. Okay, so if our alpha is 0.01, so we need to excuse me, sorry. So we need to divide this by 2, okay, because we have for the left-tailed and the right-tailed. For a two-tailed, okay, for a two-tailed test, okay, so we need to divide this by 2. So we have 0.01 divided by 2. So our alpha, so 0.005. So next step is we need to find a certain value, okay? Like I said, if we have two-tailed, let's start with the negative, then assume that the positive is in the right side, okay? So let's find a certain value in the negative z table that is closest to 0.005 but less than, okay? So let's go to the z table. So we have negative, so we need to find a certain value that is closest to negative 0.005. Okay, so we have here, so we have this value. So we have 0.00494. So it is under negative 2.5 and 0.08. Therefore, the value of our z critical is positive negative 2.8. And next, we need to calculate the test statistics, okay? So, as we observe the problem, okay, there is no value of x, okay? There is no successes, but we have this 37%. So, this 37% is automatic our P, okay? This 37% is automatically our P hat. Okay? So always remember, in terms of proportion, like I said last time, if there's two percentages, the one is for the proportion and the one is for the P hat. Okay? And always remember, our P hat, okay? So our P hat is less than our P. Okay, remember this condition. Our P hat is less than P. So if we have two percentages in the problem, automatic, the smaller one is your P hat and the bigger one is your proportion. Okay? So let's calculate the test statistics using the formula. Like I said, so we have Z is equal to P hat minus P all over square root of PQ all over N. Okay, so we have this answer, negative 0.6124. Like I said earlier, we will depend on the value or the symbol or the sign of our z-test or any or t-test. So in this case, we have negative. Therefore, we will use the negative value here in our two-tailed. Okay, so we will observe this. So what is the value of our test statistics? So we have negative 0.6124. And the value of our z-critical is negative 2.58. Okay, like I said earlier, the value, it's much bigger in terms of negative, okay? The value that is closest to 0 or closer to 0 is the bigger value, okay? Or the larger value. Okay, so in our case, our critical region is negative 50. It starts from negative 58 onwards to negative infinity. And the value of our z-test is negative 0.6124. Okay, so what is our decision here? Okay, the value of our z-test, okay, is not in the region of our critical region. Okay, therefore, we can conclude that this relationship or our null hypothesis will be failed to reject because the value of our z-test value is not inside the critical region. It is outside the critical region. Okay, and also we can prove this because of the p-value condition. What's the value of our p-value? So we have 0.5403. So we can solve this by using the method that I discussed earlier. Okay, so just use the calculator to get this value. Okay, so the value is 0.5403 and the value of our alpha is 0.01. Therefore, the value of our p-value is greater than our alpha. And like I said, if the value of our p-value is greater than alpha, we failed to reject. Therefore, based on our assumptions and based on our calculations, okay, we are failed to reject the hypothesis here because the value of our z-test is not in the critical region. Okay? Or that's so. Okay? And for our last topic, so hypothesis testing for the variance and standard deviation. Okay. So the x squared test for a variance or standard deviation is a statistical test for a population variance or standard deviation. The x squared test can be used when the population is normal. So the x squared test is also what we call as the chi-square. Okay, so the x squared test, the table that we need to use in terms of x squared test is the chi-square table. Okay, so the test statistic is s squared and standardized statistic is the formula here. So we have x squared is equal to quantity n minus 1 multiplied by s squared all over sigma squared. So follows a chi-square distribution with degrees of freedom n minus 1. So in terms of chi-square, we are using n minus 1 as our df. Okay? So example number 1, find the critical value for a left-tailed test. Okay? So we are going to find the critical value for a left-tailed test when n is equal to 19 and alpha is equal to 0.05. So we need to find x squared left. So we already know how to solve this problem. Okay. In terms of x squared left, always remember that we have a formula for x squared left. So x squared left is equal to 1 minus alpha. Okay. So 1 minus alpha. Is it correct? Okay. So find the critical value for left-tailed tests. Okay, so they are 18 df because df, okay, so df is equal to n minus 1. Okay, therefore, we have 19 minus 1. So our df is equal to 18. So the area to the right of the critical value is 1 minus alpha. So let's find the df here. So we have 0.95. Okay, so from the table, so let's find the critical value of 0.95, 18 df. Where's the chi-square? So 18. So our 18 here, 0.95 for the left. So we have 9.95. 0.390. Okay? So we have, is it correct? So we have, sorry, where's my presentation? So we have 9.930. Okay? That's basic. Example number 2, find the critical value for a two-tailed test when n is equal to 26 and alpha is 0.01. So our DF automatic, so DF is equal to n minus 1. So we have 26 minus 1, so DF is equal to 25. So the areas for the left or right of the critical values are 1/2 alpha. Therefore, we have 0.005 for the okay, so we have 1 for the right and the left. Okay, so we have 0.005 and we have 0.995. So this is for the left and this is for the right. So let's look at the table. So I think my table is not complete. So if we look at the table, a certain chi-square with a certain value, so we will come up with these answers. Okay, so just verify it if you have uh, a chi-square table with DF up to 30 or more. Okay, so it's not important. This part, this is the most important one. Okay, so a college professor claims that the standard deviation for students taking a statistics test is less than 30. 10 tests are randomly selected and the standard deviation is found to be 2.28.28. Test this professor's claim at the alpha is equal to 0.01 level. Okay, so our null hypothesis here is, so our alternative hypothesis here is we have standard deviation less than 30. So our standard deviation is less than 30. Therefore, our null hypothesis is standard deviation is greater than or equal to 30. Okay? Then our S 10. So our N is 10. Our S is equal, our mu, I mean the sigma is equal to 28.8. Okay. Then alpha is 0.01. Okay. So so we already specified the null and the alternative. So find the critical values. Okay. So we have alpha 0.01. Okay. So our DF is 9. So we, in terms of left-tailed, so like I said, if we are going to find the left-tailed, we will subtract the value of alpha from 1. So 1 minus 0.01. So we have 0.99. And as our alpha and our DF is 9. So let's look at the chi-square table. So we have 9 and 0.99. Am I correct? So we have 0.99 and DF9. So we have 0.99 here and DF9. So the value is 2.088. And we are in left-tailed test, therefore the value is negative. Okay, so it's positive. But okay, in terms of standard deviation, it's not like the mean that we are depending on sides. So in this case, we have positive. So we have 2.008 for the left tail. So let's calculate the test statistics. So we have x squared. So x squared is equal to n minus 1 multiplied by s squared all over sigma squared. So our s squared is our critical value computed. So 10 minus 1 multiplied by 28.8. Oh, wait. Oh, sorry. Our test statistics is 28.8. Okay. And our standard deviation. Okay. Our standard deviation is 30, or our sigma. Okay. So this is S. Let me just clarify. So this is S. Sorry. So this is S. And our standard deviation is 30. Okay. So compute it. So we have 8.2944. So in terms of chi-square test, okay, the p-value method can be only applied on z-test. Okay, so we will just skip this. Okay, so the value of our test statistics is 8.2944, and the value of our critical value is 2.008. So what's the value of our z critical value? Okay, so we have critical value. So I think we should use negative here. So wait. Okay, no. So we have the value of x squared test. Okay, 8.2944, and the value of our z critical is 2.008. Okay, is it inside the critical? Okay, so let's. So since x squared test is greater than, okay, our x squared critical, so we are failed to reject our null hypothesis. Okay, so that's the claim that we can decide. Okay, so the critical region is 0 to 2.088. Okay, okay, so we can conclude that if x squared test, okay, is greater than x squared critical, we are failed to reject. On the other hand, okay, if our x squared test is less than x squared critical, we are going to reject. So that's all for our part 2. So if you have any questions, just message me in MS Teams and I will answer your questions. Thank you everyone and keep safe.